Hello students, welcome to my YouTube channel Concept Tech 2018. I am Dr. Sunanda Manke and this video is a part of the series on online electronics laboratory, and in this part we'll discuss the lab exercises on signal generators. The assignments in this part includes the oscillators. Here we'll cover both RC and LC oscillators. In multivibrators, we'll do experiments on all the three multivibrators: bistable, monostable and astable. And we'll see the working of 555 timer as monostable multivibrator and as astable multivibrator. The first assignment is RC oscillators. In RC oscillators, we'll see Wein bridge oscillator. As you can observe here, the Wein bridge oscillator is having two RC circuits. It is termed as lead and lag circuits. One is series combination of RC and one is parallel combination of RC, and they provide feedback, positive feedback to the operational amplifier, and negative feedback is given using these R1 and R2 resistors. And Wein bridge oscillator gives sinusoidal output waveform when we observe it on CRO. This experiment we'll do in the virtual lab. Let's do the experiment on virtual lab. This is Electronics Communication Engineering lab. Clicking on list of experiments gives us all the experiments, and we'll go to Wein bridge oscillator experiment here because it is an RC oscillator. And the page here shows the theory, procedure and simulation. We'll go to simulation, and this shows the Wein bridge oscillator circuit using operational amplifier. We'll do the connections. Output is connected to the oscilloscope. Being oscillator, we do not need to apply any input signal. We'll just switch on the power. We have checked the connection. Connections are okay. So what we have to do is we have to switch on the power and the circuit will start oscillating. This is parallel and series RC circuit here, and these two are the additional resistors for feedback. Now we'll start the experiment. In this experiment, this resistor is variable. So by varying the value of this resistor, we'll obtain different frequencies at the output. We'll switch on the power and now we'll observe the waveform here. We have to change the value of R1, and you can observe by changing the value of R1, the frequency at the output is changing. The value of the capacitor is constant to 0.1 microfarad as you can see in the table, and the resistance value is changing, and thereby the frequency at the output is also changing, and it is decreasing with increase in the value of the resistance R1. We'll increase the value of R1 further, thereby we can tabulate the different frequencies, and when we plot it, we are not able to observe the sinusoidal waveform. It is because it is plotting all the frequencies in one graph. Now what we can do is we can reset and we can do the experiment again. Checking connections will give us the connections are okay, and we'll start the experiment again. This time we'll take just one or two values of R1 and then we'll plot. Now if we plot it for this value of R1, you can observe the output. It is a sinusoidal output here, and the frequency is as observed in the table. It is 1.4 megahertz. And thus this oscillator is working as Wein bridge oscillator. The second oscillator is twin-T oscillator, and this experiment will be performed on the oscillator kit. In twin-T oscillators, we have two RC circuit. One is low pass and one is high pass. You can observe here two resistor and a capacitor, two resistor and a capacitor, two capacitor and a resistor, two capacitor and a resistor. So this is the feedback circuit which is used in twin-T oscillators. We'll simply switch on the power and we'll observe the output of this oscillator at this position. We have to change the switch position for 20, and the oscillator output is obtained on the CRO. We have set it to 500 microseconds, and it is approximately taking 1.8 divisions 200 microseconds and it is taking 4 divisions, right? In 500 microseconds it is taking 1.8 divisions. We have observed in 20 oscillators that a sinusoidal output waveform is obtained, and the time divisions, if we see, the one cycle requires 1.8 divisions at the time division setting of 500 microseconds, which gives us the time period of 900 microseconds, and the frequency obtained for this 20 oscillators is 1.1 kilohertz, and the amplitude which was observed on the x-axis, it was 4 volts peak to peak. The theoretical frequency calculated by the components which are connected in the circuit, that is RC, resistance and capacitors, the theoretical frequency is 750 hertz, and you can see the difference between theoretical and practical frequency. It is because of the tolerance of the component values as well as error in the calibration of the meters which are used in the laboratory. I hope you have understood how Wein bridge oscillator and how 20 oscillator works and how the frequency is calculated on the CRO for the 20 oscillator.